My talk today is on distributed strategy selection, and our approach towards it is a submodular set function maximization. My faculty advisor is Professor Kia. Let me start with a simple example, the example of area coverage. Let's say we have several sensor placement locations in a city, and each sensor placement location has its own importance. For example, downtown area is more important to be surveilled, and then the suburb area is not as important. And we have a set of 4 different sensors providing different levels of coverage. One way of placing these sensors could be placing all of them in downtown area, but they have a huge overlap with each other and not necessarily providing extra amount of information. Another way of placing these sensors could be like this, placing 2 small sensors in downtown area and placing the largest sensors in suburb area. But still, it cannot be the most efficient way of doing it because the two small sensors are not covering the whole downtown area, and the downtown area, as we said, it has more importance than the other areas. Another way of placing these sensors could be as it's shown, but it's not still as efficient. As you can see, 2 of the sensors have a huge overlap with each other. So the sensor placement problem or area coverage problem can be formulated as maximizing placing the sensors in an area, and the way that we show that is by set R. So set R shows how the sensors are placed, and they should belong to a feasible set I. It means that, for example, first sensor can belong to any of the placement points times second sensor can belong to any placement points, and so on. So these kind of problems, they can all be formulated as a form of maximizing a utility function of the final strategy set. The strategy set can belong to a ground set, and it can be regulated as if it belongs to another set I. In this talk, we are considering the constraint set I to look like this. It means that if the ith sensor placement, all possibilities can be defined as Pi, the final strategy set can only have that ith sensor being placed only in one location. And we also consider that the utility function is a submodular set function. So we're pushing this problem one step further. We want to solve this problem in a distributed way. So for example, let's say each sensor is smart, and through communication with other sensors wants to find its best placement location and move there. So the final best strategy set could consist of the first sensor finding its best placement location all the way to the nth sensor finding its own best placement location. And they should come up with these bests through communicating with each other. So in this talk, we are dealing with submodular set functions. A set function is a set from a power set of a ground set P to a real value, and we're assuming that our set functions are monotone increasing, meaning that if P1 is a subset of P2, subset of the ground set, then utility of P1 is less than or equal to utility of P2. And also we're assuming that the set function is submodular. So if we define this function delta f of p given p bar, it means that if we have p bar, which is a subset of the ground set, if we add the strategy p to p bar, how much more of return we're gonna get. So now if we have set p1 and set p2, and p1 is a subset of p2, and also the strategy p is not in p2, meaning that like P1 is the smaller set than P2, then if we add that strategy P to P1, we're gonna get more return than when we're adding it to set P2. There is a challenge in finding the optimal solution to a set maximization problem when given a ground set and also the constraint. The challenge is that solving these kind of problems is NP hard, meaning that as the size of the ground set increases, the number of operations that's needed to find the strategy set, the optimal strategy set, R star, increases exponentially. So there could be an alternative way of solving this problem. So if you can find another set R bar that we can guarantee that its value is more than alpha times the optimal value of this maximization problem, and we can find this R bar in polynomial time, that could be promising too. So a way of finding a suboptimal solution in polynomial time is doing sequential greedy. Sequential greedy starts with an empty set. For example, let's consider the area coverage problem. So we have the empty set, and then we place the first sensor such that the utility of placing that sensor is maximized, given that no other sensor is already placed in the area. And then after placing that, we go to the second sensor. Then we place the second sensor, given that the first sensor is already placed, and we want to place the second sensor such that its utility is maximized. And then we go over and over in this loop such that we are placing every sensor that we have. So essentially, we get a sequential greedy strategy for the sensor problem, and the utility of that placement is at least half of the optimal solution. Sequential greedy is really straightforward to be decentralized, given that the sensors are smart, and over the communication graph we already have a preset sequence that sensors or the agents can communicate over that. Then we can just implement the sequential greedy. The first sensor can choose its location, the best location that it fits, and it can go sit there and communicate the location to the second sensor, and second sensor can decide on its strategy, and so on. The problem with that is that the sequence should be preset and it's not robust to network failures. And also there is another question that if we can do better than 1/2. So to solve the problems that I stated, we can move to a continuous domain, specifically multilinear extension function f that goes from hypercube n to real values. So we have membership probability vector n of size n, and each of the entries shows the probability of one strategy happening, and we can rename the strategies from 1 to n. And essentially what multilinear extension given membership probability vector does is that first, given a set R, it calculates the probability of that set happening, and then we do an averaging over all possible R's given the ground set. So the problem with this multilinear extension is that to calculate this function, we have to know the utility value for every subset of the ground set P, and it's already NP hard to calculate. But we can solve this problem. So we assume that we have a value oracle that given strategy set, we know the utility value, and then based on that, the multilinear extension can be interpreted as expectation of the value of given a strategy set that was sampled from the membership probability vector. So we have this interpretation, so we can have an estimate of f of x by doing sampling. Also, we can calculate the gradient of f of x, again, by sampling. So essentially what multilinear extension means is that instead of having a strategy existence in strategy set R to be 0 and 1, we extend the probability of existence of a strategy says anything between 0 and 1. So the bridge between the continuous domain and the discrete domain is that if we have the optimal strategy set R star maximizing the utility function, and we have the X star maximizing the multilinear extension function, then X star is going to be a vertex of convex hull, and X star being a vertex means that it has only entries of zeros and ones, and wherever we have a 1, it means that a strategy is in the optimal strategy set R star. So now we get to the constraint part. So we had the constraint that each sensor had to be placed in only one of the possible placement locations. Now if we want to translate it into continuous domain, we have a convex hull that looks like this. So it means that if we have the probability vector x, then for the x sensor, the entries that are specifically related to placement of that sensor to the possible locations, the sum of the probabilities should be 1 or less than 1. So essentially, if we optimize the multilinear extension subject to this convex hull, then what we will end up with is a vertex of this convex hull. So that vertex is a vector that consists of zeros and ones. And wherever that there is a 1, we put that strategy in our optimal strategy set. And essentially, we're going to get R star with that, which is the outcome of optimizing the set function subject to this constraint. So as we talked, finding the optimal solution for the multilinear extension can lead to finding the optimal solution for the set function maximization. However, the problem is that the multilinear extensions, finding the function itself is NP-hard. So what we can do is find a vertex of the convex hull, X bar, that we can make sure that it has an optimality gap of alpha, and from that vertex, because it has entries of zeros and ones, we can end up with the set R bar with optimality gap of alpha. There is one property of multilinear extension that can help us in finding that X bar, and that's this. If we have one of our star, meaning that we have a vector of ones and zeros, that we have one for a strategy that belongs to our star, times the gradient of f of x at a given x in the convex hull is going to be more than the optimal value minus the multilinear extension at that x. And essentially, we can solve this optimization problem and get v of x. Now that we have this v of x, we can make sure that v of x times the gradient is going to be more than the optimal value minus multilinear extension's value at that x. And then if we start at 0 and integrate both sides from time 0 to time 1, we're going to get this equation here. F of the trajectory x at time 1 is going to be more than 1 minus 1 divided by e times the optimal value. So this is our alpha. And then the trajectory at time 1, it's going to end up at the edge, not a vertex. And finally, with a lossless rounding method, like pipette rounding, we can go from that point on that edge to a vertex. So we can get that x bar we were looking for, and it's going to have the optimality gap of 1 minus 1 over e, and it's clearly better than 1/2. So with what we established so far, we can go ahead and propose our distributed gradient ascent algorithm. So in this algorithm, each agent has its own local probability membership xi, and this xi consists of the agent's local belief on its own local strategy set xii, and also it has an estimate on other agents' belief on their own local strategy sets. Given xi, agent I goes ahead and does one step of local gradient ascent. What local gradient ascent step does is that agent I goes ahead and based on xi, which is its own local belief on the whole strategy set, it chooses the best strategy among its own local strategy set that suits the best in that step, and it increases its belief on that strategy with the amount of 1 over t. However, there should be a way of agent I know about the updates of other agents. The way of notifying other agents over network about their local belief can be done through a maximum consensus. So in maximum consensus, each agent transmits its own locally updated belief to the network, and through the maximum consensus, they update the final local belief in that step. And what it means is that each agent trusts other agents on their own local belief. So starting from 0, each agent updates its belief through update and communication, and does that for capital T steps. And essentially, the trajectories may not reach an edge of the convex hull. However, if we take the maximum of all beliefs for all agents, we can get the vector x bar, and we can make sure that at time capital T, this x bar is going to reach an edge of the convex hull. X bar reaching the convex hull is a property of maximum consensus, and later we will see that it facilitates the distributed rounding. So from the edge we can get to a vertex. We already had the central solution, the continuous central solution, knowing that it's going to reach the edge of convex hull. But now we have the distributed one, and because of some errors, it's not going to exactly land where the central solution lands. The first source of mismatch is network delay. When an agent updates its local belief and sends it to the network, it's gonna take at most dg, which is diameter of graph, steps to reach other agents in the network. The other source of mismatch is going to be sampling efficiency. As we said, calculating the gradient of multilinear extension is NP hard, so we do sampling. So we're not gonna have exactly the gradient. The other source of mismatch is the discretization error. When we studied the central solution, it was in continuous time, but now each agent updates its own belief every 1/capital T of time. Now, when we put it all together for the optimality gap, we see that we have the term 1 minus 1/E, but we have another term that comes from all these three sources of error. However, we are not quite done yet. This X bar of capital T is a point on the edge of the convex hull, and it's not an explicit policy yet. We know that X bar is on the edge, and we want to get to a vertex of the convex hull. But each agent has only access to Xi, its own local belief, and doesn't have access to X bar. So Xi may not land on the edge of convex hull, but the agent has to decide on a local strategy based on its own local belief, which is Xi. Based on our distributed algorithm, we can make sure that Xi of t, which exists in both Xi and X bar at time capital T, is going to have entries that sum up to 1. What we propose is that considering an interval between 0 and 1 and dividing that interval to subintervals, each of them equal to one entry of xii. Then agent I generates a random beta between 0 and 1 and locates where it lands in the interval between 0 and 1. Based on where beta lands, agent I says that, okay, I'm going to make that entry on xii to be 1 and the rest are going to be 0. And then the one, that's going to be my strategy. Essentially, each agent is choosing randomly its own local strategy set, and when we put it all together for all agents, we're gonna get R bar, and the expected value of this rounding is going to be more than f of x bar of capital T, which we had the optimality gap for it. So for our numerical example setup, we have 5 different sensors, A, B, C, D, and E. They are non-homogeneous. Also, we have these gray dots as the possible sensor placement locations, and also we have the red dots. And we want to place the sensors such that they're covering as much as red dots as they can. So when we compare our algorithm with sequential greedy, we see that our algorithm spreads the sensors in an efficient way, but in sequential greedy, it really depends on the sequence that agents go ahead and choose their location. So for example, on the first one, we see that there is a huge overlap between the sensors, which is inefficient. And then this table shows the number of samples, the utility of our algorithm, based on the number of samples and based on the number of intervals that each agent does the update. And we can see that as k increases, as capital T increases, we get a better utility.